Welcome and hello. This is a video lesson in RIMS, and in this lesson, we're going to be covering reservoirs, as well as a few other related topics such as storage zones, units, unit conversions, and offsets. All right, so let's go ahead and get started. I've got RIMS up on the page right now. I'm also going to bring up a schematic of a reservoir, something very simple and basic, doesn't get simpler than this. We have an inflow into the reservoir, we have the triangle reservoir symbol, and then we have an outflow. If we're going to go ahead and assign specific variables to this reservoir, we can use reservoir 1, for instance. We'll call it res 1. So I underscore res 1 would be the inflow to reservoir 1. S underscore res 1 would represent the storage or the current quantity of water in the reservoir. So that's a decision variable. Inflow would typically be a state variable. And then O underscore reservoir would be the outflow or the release from that reservoir. Also, definitely a decision variable. Let's go ahead and define these variables now in the Russell file and then tie them together with continuity constraints and then objectives ultimately. All right, so let me bring up a file here. This is going to be a reservoir.russell file. You can name it whatever you want. Then I'm going to go ahead and paste in the definitions for the two decision variables, which is the current volume or storage of water in reservoir 1, S underscore res 1, and then below that, the actual release or the outflow, capital O underscore res 1. Notice that for the storage, the kind is storage and the units are in TAF, that stands for 1,000 acre feet. So for instance, the value was 10, that would represent 10,000 acre feet of storage. If it was 50, it'd be 50,000 acre feet of storage. And then down here for the reservoir release, this is a kind channel, and then the units here are in CFS. Sometimes you may want to keep all your channel decision variables in a separate channels.russell file, but there's no problem with defining them right here with the reservoir if that's what you want to do. All right, so already we noticed that we have two different units here. We have 1,000 acre feet and CFS, and we're going to address that a little bit later. Let's move on to an inflow file. So I've got inflows.russell here, and then here is the state variable that calls the inflow data. This is calling a table. The table is called res1 underscore inflows, and then the column with the actual inflow data is right here. It's just labeled inflow. This table of data, res1 underscore inflows, would be saved in a different file inside the lookup directory. So in your file structure, you'd go up to run and then into the lookup directory, and then you'd want your file to be named the exact same thing as the table, res1 underscore inflows. And then here is some example data. I'm going a little bit fast. This lesson is not about reading in text files, but if you want a deep dive on how to do this, check out my lesson 9, reading input from text files. I'll leave a link to that video in the description of this video. But anyway, we've got a couple lines of comments, and then the first line here is the name of the table, and then the columns are tab separated. So month and then inflow. Here are some typical inflow values for the 12 months of the year. And then the inflow is in CFS. Now, I could have also defined this inflow with a time series data, not a table lookup. So there's two different options to define your inflow time series data. So to tie all this together, we have our inflow, we have our storage, and then we have our outflow. We want to create a constraint, a continuity constraint that relates these three variables together. And to do that, we'll go to perhaps a constraint file right here. It's called a goal, but it's really a constraint, continuity underscore res1. And what I'm doing here is I have the sum of the inflows minus the sum of the outflows equals the change in storage right here. So this is your inflow, that's the state variable, we just defined that. This is the decision variable for the reservoir release. And then as I mentioned, this term right here on the right-hand side is the change in storage in the reservoir. We've got a few new terms here, like this TAF underscore CFS. We see that twice. And that's going to be our conversion from 1,000 acre feet to CFS based on the specific time step that's used in the configuration. Page 30 of the Russell Plus reference manual, at least the version I have, shows a number of intrinsic functions. And the second one down is the one we were just looking at. TAF underscore CFS returns a multiplier that converts a given quantity of 1,000 acre feet per the time step to cubic feet per second, where you don't have to use the offset. And if you don't, it's just assumed to use the current time step. Okay, so what that means is TAF underscore CFS is just a conversion factor. All right, the other term I wanted to explore was this offset right here. So this first term is the storage of water in reservoir 1 converted to CFS at the current time step. And then this right here, this term is the storage of water in reservoir 1 converted to CFS in the previous time step. So this -1 value here is an offset for the storage value, this decision variable, from one previous time step. So if your time step is 1 month, then it's from the previous month. Near the bottom of page 28 in the Russell Plus language manual, we have previous and future time step values. In state and goal statements or constraints, you may reference decision variables, state variables, aliases, and input time series variables up to 12 time periods prior or ahead of the current time period by using this offset notation. So it gives a couple examples down here where storage 11 and then in parentheses -2 refers to the storage 11 2 time steps ago. Inflow 10 and then in parentheses 4 refers to a variable inflow 10 4 time steps into the future, with a couple more examples right here. All right, so that's what's happening with this constraint. This is our continuity at the reservoir. And that's basically it for reservoirs. That's the most basic lesson I can provide. I will mention a couple other things since I mentioned zones in the intro. So say, for instance, you're ready to level up and make your reservoir have multiple zones. This is not uncommon. I'm going to go back to the reservoirs.russell file where we define the two decision variables of the storage and the outflow, the release. I'm going to go ahead and paste in some more code. And I've added a label just for all of them, so it's pretty easy to make sense of it all. I've got 3 state variables here. This is the capacity in zone 1, zone 2, and zone 3 of reservoir 1. And as you see, I'm just setting it to a state variable. It's a simple state variable, and 10 here represents 10,000 acre-feet of storage in zone 1, 90,000 acre-feet of storage in zone 2, and 20,000 acre-feet of storage in zone 3. A zone 1 would probably be like the bottom, like an inactive zone, a dead zone. Zone 2 may be like a conservation zone, your main usage zone, and then zone 3 may be the highest zone, something that's like flood control, for instance. So the exact purposes of your zones and the size of the zones, that's totally up to you. I'm just giving a basic example of how it works. Below the zone storage capacity, I've got 3 more decision variables I've defined here, and this is the actual volume of water in each of the zones. So S underscore res 1 underscore 1 represents the current volume of water in zone 1. Same thing with zone 2 and zone 3. So the total volume of water in the reservoir would be the sum of the volume of water in each of the 3 zones. The same way the total capacity of the reservoir would be the sum of the capacity of each of the 3 zones. Now, what I've seen done a couple times is, for instance, Z2 would represent zone 1 and 2. So as I've described it here, the total capacity is 10 plus 90 plus 20. That's 120,000 acre-feet. However, I have seen it described a separate way where zone 2 represents the top of zone is the capacity of zone 1 and 2 combined. In that case, it would be 100, right? And then zone 3, that would be the top of capacity of zone 1, 2, and 3 combined, in which case that would be 120. So, however your modeler and your team are setting up your reservoirs and defining your zones and capacities and so on, just go ahead and do what they do. But I myself haven't decided how I want to do this as a standard. So I'm just trying it a few different ways. I will link a WRIMS exercise 4 basic reservoir example in the description of this video. And in that video, I do it that other way, where I have the total capacity, and I also am using an S right here instead of a C for capacity. So just so you know, that one's done a little bit different, but I'm going to go ahead and set this back to what it was. Okay. With these additional variables of the capacity and the volume within each zone, we also need to specify a few constraints. So I'm going to go back to my constraints.russell file, add a new section here for reservoirs, even though the mass balance was a reservoir as well. Here it is, reservoirs. And this constraint we see on line 5 here is just the total storage. So the total storage of reservoir 1 is the sum of the storage in each of the 3 individual zones. And then in lines 6, 7, and 8, this constraint basically says that the current storage of water in a specific zone cannot exceed the capacity of that zone. So again, if I define the capacity of zone 2 as really the capacity of zone 1 and 2, in that case, you'd have to subtract zone 1 from zone 2 on the right-hand side here. So just be careful about that. Different modelers probably do it different ways. All right, and the very last part of this lesson is to set some objectives. So say, for instance, we want our water to be at the top of zone 2. Therefore, we maintain 100,000 acre feet of water, but have an extra 20 for flood control. In that situation, we can set an objective of something like this right here, where we have objective equals, and then our 3 decision variables for the amount of water in each zone. Zone 1, Zone 2, and Zone 3. The highest priority is to keep Zone 1 filled. That's why it has the highest weight. Next, another positive coefficient to the objective function value is 20. That's for Zone 2. And then I'm actually assigning a negative weight to this coefficient that's associated with the decision variable for the amount of water or the storage of water in Zone 3. Okay, so that should keep the reservoir right at the top of Zone 2 at about 100,000 acre feet. And then we can tweak these weights as other decision variables are added to our objective function. All right, well, that was it for an introduction on reservoirs and how you can use them in RIMS.